Okay, everyone, so we're starting Unit 3, looking at energy changes and rates of reaction. So this is Chapter 5 and 6 in your text. Energy changes so we're kind of getting into more math-based chemistry. So the first 2 units is very theoretical or looking at reactions and properties. We're kind of moving more now into physical chemistry. So actually this entire unit is based on the unit of physical chemistry. So you can take entire courses in this, you can take entire degrees in this. Usually this is matched up very nicely for those of you who are thinking about going into, or you are going into like an engineering type field. Okay, so please make sure you have a calculator. The reference sheets that I had posted, please make sure that you have a copy of that handy with you when you're trying to work through some of these questions. Yeah, so essentially as we go through this, you need to have that and the periodic table handy. Okay, so so as I mentioned, we're looking at thermochemistry. So it's a study of not only looking at chemical processes, but physical processes as well. So meaning a change of state or dissolving. It doesn't have to always necessarily be a chemical reaction, but the main thing is we're looking at the study of energy changes in those processes. So, what forms does energy come in? So it comes in many forms, but the 2 that we're going to be looking at are essentially kinetic energy and potential energy. So kinetic energy is the energy of motion or movement. So when we're talking about particles that have kinetic energy, it's essentially referring to the actual movement of those atoms or of those molecules. So for example, when we start looking at temperature change, right, you're changing the kinetic energy of a molecule when you increase the temperature because they're simply moving more, okay? Potential energy, this goes back to, if you remember from way back when in grade 9, I'm not sure if grade 11 physics you talk about this at all, but it's talking about stored energy, right? So this can be, for example, imagine you have an apple that's in the tree, right? It's not going to fall to the ground, but it has the potential to fall a certain distance if it were to fall. So it's talking about energy that hasn't yet done anything, but it has the potential to do something. So in terms of for chemistry, what are we going to be referring to? Let's say we were looking at, let's say I have a molecule here. The bond energy, so a bond that's between atoms, has a certain amount of potential. So meaning if we were to break that bond, it will give off a certain amount of energy. So we're going to talk a lot about energy changes in reference to chemical energy when we're looking at bonds breaking and bonds being reformed. So let's take a look at a reaction, just some kind of key things to start getting to know. So now when we start looking at chemical reactions, you may see energy terms actually being in the balanced chemical equation itself. So here we have a combustion reaction of acetylene or ethine, but you have a triple bond there. But energy is released. Okay, so when energy is being produced in a reaction, we can sometimes actually write it as if it is a product. So if you see energy being on the product side of a reaction, that's indicating that we have what's called an exothermic process. So meaning the energy is being given off around that particular process. So energy is being given off to the surroundings. Let's say you had energy that was on the reactant side. Okay, so if energy is a requirement for that reaction, that means it would be written on the reactant side, and you would have an endothermic process, which means energy has to be absorbed in order for that reaction to happen. Okay, so another point to bring up is, I know here we have literally the word energy. Instead of the word energy, you can also see an actual value. So for example, maybe I have here 50 kilojoules. So this whole thing is making, 4 carbon dioxide, 2 water, and then 50 kilojoules worth of energy. So again, if it's on the product side, it's exothermic. If we had that energy amount written as a reactant, it would be endothermic. So when we're talking about energies in chemical or physical processes, we're going to refer a lot to these two terms. Okay, so we have something called a system and something called the surroundings. Okay, and obviously the two together make up the universe. Okay, so meaning everything, all energy that is in this universe, we can look at it as being the system that we're focused on, plus kind of everything else around it. Okay, so the system is the sample or process being observed. So this could be, let's say we have inside of a test tube, let's say in here I had a piece of magnesium, and I'm going to put that in hydrochloric acid, right? Let's say this is hydrochloric acid. So the system itself would be the hydrochloric acid and the magnesium. The surroundings is literally everything else. So it would be the water that hydrochloric acid is in, right? The solvent, the test tube itself, the air around it, right? So it's literally everything else. So when we talk about the system energy, we're talking about the energy of the process itself. When we talk about surrounding energy, we're talking about everything else. So when we talk about changes in energy, we're looking at the interactions between these two. What is the energy being released to the surroundings, or what is the energy being absorbed from the surroundings to the system? So it's either going one way or the other. The system is either releasing it to the surroundings, or the system is absorbing it from the surroundings. But there is an exchange of energy, and sometimes an exchange of matter as well. So there's 3 different types of systems that we're going to be looking at, some more closely than others, but it's important that you know the differences between them. So we have an open system, a closed system, and an isolated system. So an open system is where you have the ability to exchange both matter and energy. Okay, so imagine like we're boiling these potatoes and we have water that's evaporating. So water is able to evaporate and leave this pot, right? I can also use this, stove to heat up the water inside of the pan, right, inside of the pot. So like energy can go in and out of the pot, and the water can go in and out. And you know what? If I had another potato and I wanted to throw it in the pot, I could do that because it's open. A closed system is where energy can be exchanged, but not matter. So meaning an example here, right? Let's say we're doing the same thing, but I have a lid on my pot. So energy can go into the pot, but I cannot have any water evaporating, and I can't put another potato in because the pot is closed, right? It has a closed lid. So let's say we're talking about this in terms of chemistry. If I had a test tube with that same reaction happening we were referring to before, if I have this as an open test tube, right, that's an open system. If I were to put a stopper in here, right, that's a fantastic stopper. But let's say I were to close the top of the test tube with a stopper, well, now I would have a closed system, right? So it depends on what the process is, of course, on like what the goal is you're trying to accomplish. So the third type of system is called an isolated system. Okay, so what that means is there is no exchange of matter or energy. So this would be, let's say you have a system that's in a vacuum that's in concrete. Okay, like a concrete vacuum sealed area. Okay, so isolated systems are nice to kind of envision or think about theoretically, but this is not really possible. Okay. For the most part, a lot of systems require to be open, especially if you are boiling water. Let's use this exact example. If you're boiling water, the water usually needs somewhere to go, or eventually this pot would basically boil over. Like it's not a reasonable expectation to have a closed system, even for that matter here. Some reactions might require oxygen. So we can't really have this happening in a vacuum sealed area because oxygen needs to be available for it to react. Like, not only that, this is unsustainable. Like, how are we able to keep this vacuum continuously going, but also be able to monitor the reaction on the inside? So like, it's theoretically, we're going to talk about isolated systems, but in real life, it's not really realistic for us to do a chemical reaction in an isolated system, okay? So this is exactly what the mention is here. So it's impossible to really prevent energy from going in and out. So we are going to make an assumption that we have isolated systems, but we are not going to actually ever really have that as a realistic thing. Okay, so calorimetry. So calorimetry is kind of a branch of thermodynamics or of thermochemistry that focuses on looking at energy changes in terms of looking at heat change. Okay, so it's called calorimetry because one of the types of units of energy you can have is a calorie. Okay, so calorie, you're probably more familiar with looking at calories when you're looking at maybe the back of a food label where it says, you know, I don't know, a granola bar is like 100 calories or something, let's say. So those calories, we are going to like look at this, but in terms of the unit we will be using, we're going to be using the SI unit of energy, which is a joule. So if you remember, that's like the standard international unit. Calorie is actually more so used in industries where you want to express energy, where maybe people may not know what a joule is. Okay, so for example, like any person going in the grocery store, you know, the regular everyday person can understand the term calorie. They know that they'll have to have a certain amount of energy in a day. They know how many calories to consume. You know, if you were to tell someone, well, you need 57,125 kilojoules worth of energy, they may not know what exactly is going down when they say that, when you say that, right? Anyways, that's kind of where it gets its name, just for interest's sake. So the SI unit we're going to be using is a joule. So just a reminder, if you see something in kilojoules, joules and kilojoules is easily convertible. 1 kilojoule is 1,000 joules. So here's your calorie conversion in case you are interested. But the key thing here that we want to point out to is a calorie itself, kind of where it's the term of 1 calorie or 1 kilocalorie, is that it's the energy needed to raise the temperature of 1 kilogram of water by 1 degree Celsius or 1 Kelvin. So essentially, imagine you took, you know, a kilogram of water, or essentially 1 liter of water, right? So a liter of water, and we want to go from 20 degrees, right? We want to go from 20 degrees Celsius to 21 degrees Celsius. Okay, well, the amount of energy needed to raise that 1 degree is essentially the definition of a calorie. And if you take a look here, what does that mean? Well, if I wanted to take that liter of water, increase it by 1 degree, it would take 1.484, what am I saying? 4.184, oh, I can't even read, I'm sorry, kilojoules. This is how much energy it would need to do that process. So what happens if I had to raise it 2 degrees? You would need to double this, right? What if I wanted to raise it 5 degrees? You would have to do this times 5. So this is kind of the basis, and they used water as the basis also because the density is equal to 1, but that's neither here nor there. We'll talk more about this in a second when we're looking at heat capacity. But it's kind of like what that definition and what this number truly represents.